Before stepping deeper into the quantum world, it may help to pause for a moment and allow the atmosphere around us to slow down. Perhaps this is a quiet room, a late-night train, or a bed in a darkened bedroom. The place where this video is being heard is, in truth, a very small detail. Yet in a universe where observation always carries meaning, even that small choice becomes part of the story. Tonight's journey moves toward the smallest scales that nature allows. At those scales, the familiar rules of everyday life begin to loosen. Quantum mechanics is often described as something strange, confusing, almost impossible to picture, and yet those very rules quietly support the entire world we recognize. Every solid object, every breath of air, and even the distant stars all exist upon that foundation. Even when our intuition does not sense it, this is not a race through equations, nor a test of memory. It is closer to a slow unfolding, a way of observing how reality behaves when size shrinks, when certainty begins to dissolve, and when firm answers are replaced by probabilities. In that setting, particles can behave like waves. The outcome of experiments depends on how we measure them, and the universe no longer promises simple explanations. The goal is not to remove every mystery. It is simply to see more clearly what is known, what remains uncertain, and why the world around us still appears stable even though its foundations are so intricate. Part of the difficulty with quantum mechanics arises from the way it is often introduced. It is sometimes imagined as merely a theory for extremely small things, or as something intentionally made to appear strange. At times, it is even mistaken for philosophy dressed in the language of physics. In reality, however, the foundations of quantum mechanics are far more modest and practical. At its core, it is simply a formal system for calculating the outcomes of experiments. A physical system is prepared under controlled conditions. Then some property of that system is measured. The theory provides probabilities for the possible results that may appear. In this role, no scientific framework has ever achieved the level of precision reached by quantum mechanics. When applied correctly, its predictions match experiments with remarkable accuracy. Confusion often appears when the question changes. When people ask what is truly happening between two measurements, or what occurs in the moments when no observation is recorded. Here, a bit of intellectual honesty is necessary. Quantum mechanics itself, as a mathematical structure, does not attempt to answer those questions. It provides a method for prediction, not a detailed picture of the deepest nature of reality. Whether such a picture exists, and what it might look like if it does, is the source of the long debates about how the theory should be interpreted. If those debates are set aside for a moment, the simplest way to understand quantum mechanics is to look at the familiar sequence of steps in experiments preparation, measurement, and statistical analysis. First comes the preparation of a system in a known state. Atoms may be filtered so that only particles with a particular spin direction remain. A physical system can be cooled to its lowest energy level. Light can pass through polarizing filters so that only certain directions of oscillation continue onward. However it is done, the goal is the same: to place the system into a clearly defined quantum state. Then comes the measurement. The system interacts with a device, and information is extracted. A detector produces a signal, an electric current is recorded, or a photon leaves behind its tiny trace. Each measurement always produces a definite outcome, usually expressed as a numerical value. But when the entire process is repeated many times with the same preparation and the same measurement, the results are not identical. They vary from one run to the next, and this is where statistics begins to appear. Across many trials, the results gradually form a pattern of probabilities. Quantum mechanics tells us exactly what that pattern should look like. All the mathematical structures often associated with the theory wave functions, operators, abstract spaces exist primarily to perform these calculations. They are tools, And there is one important conceptual point to keep in mind. A quantum state is not something that can be observed directly. It is not a mist spread throughout space, nor a physical field that can be mapped point by point. In quantum mechanics, what is called a state is not an object existing somewhere in space. It is not a thin mist surrounding a particle, nor a kind of field that can be observed directly. In fact, it is simply a mathematical structure, a way of compressing all the information the theory allows us to say about measurements that might occur in the future. For that reason, when a measurement takes place and the state appears to collapse, it is not necessary to imagine a physical entity suddenly changing shape. A simpler view is that our predictive description has just been updated because a new piece of information has become available. Two basic principles hold this entire framework together. The first is superposition. If a system can exist in one state, and it can also exist in another, then it can also exist in a combination of both. The second principle concerns measurement. The outcome of a measurement is always a single definite value. It is never a vague mixture of possibilities. That value is selected according to precise probabilistic rules, defined by the Born rule, where probabilities are connected to the squares of mathematical amplitudes. This rule links the smooth evolution of the state with the discrete outcomes recorded by measuring devices. At this point, an important boundary appears. The equations of the theory and their predictive power are rarely disputed. What remains debated is their meaning. In practice, many physicists use quantum mechanics every day without committing to any particular philosophical interpretation. Another common misunderstanding is that quantum behavior appears only at extremely small scales. In reality, the decisive factor is not size but interference. When several processes are possible and no physical information distinguishes between them, their amplitudes combine before probabilities are calculated. The results can differ dramatically from classical expectations, but when a system interacts with its surrounding environment, that interference is gradually destroyed. Behavior becomes more familiar, closer to the classical world. This process is known as decoherence. Even the word observer in quantum mechanics is often misunderstood. In this context, an observer simply means any physical system capable of storing information in a stable form. A detector qualifies. A photographic plate qualifies as well. Human consciousness plays no special role. The deeper question is how clear and stable records can arise at all in a world governed by probabilities. Beneath everything lies a geometric structure. Quantum states exist within a complex vector space called Hilbert space. In this space, the similarity between two states is represented by the angle between them. States that are completely different lie at right angles to each other, while partially overlapping states lie closer together. In this sense, what governs predictions in quantum mechanics is not an intuitive picture, but the geometry of states. Perhaps no experiment illustrates this more clearly than the double-slit experiment. It is often considered the central demonstration of quantum mechanics. Richard Feynman once remarked that it contained the real mystery of quantum physics. The statement may be a little strong, but it was not made without reason. The setup of the experiment is actually quite simple. A source emits particles, electrons, photons, or other quantum objects. These particles travel toward a barrier containing two narrow slits. Behind the barrier is a detection screen whose only task is to record the position where each particle arrives. If our everyday intuition were correct, each particle would pass through one of the two slits. After many emissions, the screen would gradually show two large accumulation regions aligned with those openings. But that is not what happens. Instead of two simple bands, the screen reveals a pattern of alternating bright and dark regions. Some locations receive many impacts, while others receive almost none. The pattern is exactly what would be produced by the interference of waves, where peaks reinforce one another and troughs cancel out. This immediately indicates that the motion of particles here cannot be described by the simple picture of classical particles. The experiment becomes even more remarkable when the intensity of the source is reduced to an extremely low level. The particles are emitted one at a time, at any given moment, throughout the entire apparatus. There is only a single particle in motion. On the detection screen of the double-slit experiment, each appearance of a particle is clear and definite. There is no streak, no sign of a particle spreading out. It is simply a tiny point, appearing at a precise location. In the first moments, these points seem completely random, but the experiment continues. Particles are still emitted, one at a time, and slowly, almost imperceptibly at first, a structure begins to emerge. After thousands of detections, the familiar interference pattern gradually forms individual dots, assembling into alternating bright and dark bands. The strange part lies here: each particle strikes the screen at only a single location. Yet the final accumulated image carries the signature of a process that seems sensitive to both slits at once. Quantum mechanics handles this situation with a very specific rule. When a result can be reached through multiple paths that are physically indistinguishable, the amplitudes of those paths must be added together before the probability is calculated. In the double-slit experiment, if no interaction records which slit the particle passes through, those two possibilities remain completely indistinguishable. The amplitude associated with the first slit and the amplitude associated with the second slit are added together. Only after that step is the probability determined. Depending on how these amplitudes combine, reinforcing or cancelling one another, the probability at each position on the screen increases or decreases. This variation produces the alternating bright and dark regions of the interference pattern. But the picture changes immediately once information about the particle's path appears. If a detector is placed at the slits to record which one the particle passes through, each point on the screen can now be linked to a specific path. And as soon as that information exists in the physical world, the interference pattern disappears. Instead, the screen gradually fills with two smooth distributions, exactly as classical intuition would predict. What is notable is that this transition does not depend on human awareness or attention. Even the gentlest measurement mechanisms are enough to destroy interference. The pattern disappears whether or not anyone checks the data. What matters is not the act of observation in the everyday sense, but the fact that information about the particle's path has been recorded somewhere in the physical world. From here, an important conceptual boundary emerges. When possibilities cannot be distinguished by any physical record, the system exists in a coherent superposition. In this regime, amplitudes interfere with one another and produce non-classical effects. But when the possibilities become distinguishable, even in principle, the system behaves like a statistical mixture. Probabilities are then added directly, and interference disappears. The gradual loss of this coherence, caused by constant interaction with the surrounding environment, is called decoherence. It is this process that explains why quantum phenomena rarely appear clearly at the large scales of the macroscopic world. Another factor that plays a decisive role is the phase of the amplitude. Each amplitude carries its own phase, and when the relative phase between different paths changes, the entire interference pattern on the screen shifts. These shifts can be measured and predicted with great precision. Phase is therefore not merely a mathematical detail. It produces observable consequences and governs quantum dynamics. Naturally, this experiment invites a deeper question. While the particle is traveling through the apparatus, what is it actually doing? Does it pass through both slits? Only one slit? Or something entirely different? Quantum mechanics does not provide a single definitive answer. It offers a framework for calculating experimental outcomes, and those calculations work with astonishing accuracy. Different interpretations tell different stories about what might be happening, but they all lead to the same experimental predictions. The equations of the theory remain unchanged, regardless of which story accompanies them. At the center of this entire framework lies a single mathematical object, quietly carrying most of the theory's explanatory power. That object is the wave function, usually denoted by the symbol psi. Everything quantum mechanics can say about a physical system, every prediction about future measurements is contained in this description. For a particle moving through space, the wave function depends on position and time. At each point, it assigns the system a complex number. This number cannot be observed directly, yet it plays an essential role. When the square of the magnitude of the wave function at a location is calculated, it gives the probability density of detecting the particle there. Where this value is large, detections occur more frequently. Where it is small, they become rare. At first glance, it is tempting to imagine the wave function as a blurry cloud marking where the particle actually exists. But that intuition quickly leads to misunderstanding. The wave function is not a physical substance spread through space, nor is it a material object in any familiar sense. The wave function is not an object in space. It does not exist as a physical entity that can be touched or directly seen. Its role is more modest, yet far more powerful. It is the predictive framework of quantum mechanics. From this description, the theory determines which outcomes may occur when a measurement is performed and assigns a precise probability to each possibility. One feature that makes the wave function difficult to visualize is that it takes complex number values. Each value carries not only a magnitude but also a phase. This often leads to the question of whether the entire theory could be constructed using only real numbers. The answer is no. Complex numbers are not a decorative mathematical detail. They are an essential part of quantum mechanics. Two wave functions may have exactly the same magnitude at every point in space and still represent different physical states if their phases differ. This difference appears directly in interference phenomena. When amplitudes are added together, the relative phase between them determines whether they reinforce or cancel one another. If the complex phase were removed from the theory, the interference patterns observed in experiments would no longer be described correctly. Much of the predictive power of quantum mechanics would disappear with it. This reveals that the wave function carries more information than probability alone. The square of its magnitude tells us where a particle is likely to be detected, but it is the phase that governs how the state evolves over time and how it interacts with other states. Two states may look completely identical if one examines only their probability distributions at a single moment. Yet as time passes, they may spread, interfere, or concentrate in entirely different ways. Another important point is that the wave function itself cannot be measured directly. No device can read it out in a single measurement. Experiments only access quantities derived from it: probabilities, expectation values, or correlations between measurements. To reconstruct the full wave function of a system, physicists must prepare many identical copies of that system and perform different measurements on each copy. From the large collection of resulting data, the original state can then be reconstructed. This process is known as quantum state tomography. It is possible, but it requires extremely careful experimental control, repeated trials, and a significant amount of data. Even when successful, the reconstructed state is determined only up to an overall phase, because that global phase produces no observable consequences. The specific shape of a wave function also depends on how we choose to represent the system. This choice is called a basis. In the position basis, the wave function is expressed as a function of position. In the momentum basis, it becomes a function of momentum. These two descriptions are related through the Fourier transform, a mathematical operation that redistributes information between position and momentum in a precise way. If we choose the energy basis, the same state appears as a combination of energy eigenstates, each corresponding to a definite energy value. None of these representations is more fundamental than the others. They are simply different perspectives on the same physical state. Selecting the appropriate basis can sometimes transform the difficulty of a problem. A wave function that appears complicated in one description may become remarkably simple in another. This is similar to classical physics, where choosing the right coordinate system can make a calculation immediately clearer. However, regardless of how it is written, every wave function must satisfy one basic condition, since the square of its magnitude represents probability. And since the total probability must equal 1, the probability across all space must also sum to 1. This requirement is called normalization. It ensures that the wave function accounts for all possible outcomes that a measurement could produce. In classical physics, quantities such as position, velocity, or energy are typically associated directly with specific numerical values. A particle has a definite position, a definite velocity, and measurement simply reveals values that already existed beforehand. In quantum mechanics, however, the description changes completely. Measurable quantities no longer appear as simple numbers attached to particles. Instead, each physical quantity is associated with an operator. An operator is a mathematical structure that acts on the wave function and transforms it according to a specific rule. At first glance, this change may seem small, but its consequences are profound. In the quantum world, measurement cannot be separated from the way these operators act on the state of the system. For example, the position operator acts on the wave function by multiplying it by the coordinate of position. The momentum operator, by contrast, is related to differentiation with respect to position. These rules are not chosen arbitrarily. They are determined so that the entire theory agrees precisely with experimental results. When a quantity is measured, the result cannot be just any value. The possible outcomes are predetermined by the corresponding operator. They are called its eigenvalues. If energy is measured, only the eigenvalues of the energy operator can appear. No other results are possible. This immediately leads to a natural requirement. Measurement outcomes must always be real numbers. No one has ever observed an energy or position with an imaginary value. To guarantee this, operators representing physical observables must belong to a special class known as Hermitian operators. These operators possess two important properties. First, all their eigenvalues are real numbers. Second, the eigenstates associated with different eigenvalues are always orthogonal to one another. Orthogonality has a clear physical meaning. Two orthogonal states can be perfectly distinguished. If a measurement identifies the system in one state, it cannot be confused with the other. In this way, each measurement outcome corresponds to a genuinely distinct physical state. An eigenstate of an operator is a state in which the corresponding quantity has a definite value. If a system is in an energy eigenstate, every measurement of energy will return the same result. There is no randomness. However, most quantum states are not eigenstates of most observables. Instead, they can be expressed as superpositions of many eigenstates. When a measurement is performed, one eigenvalue appears randomly. The probability of each outcome depends on the overlap between the system's state and the corresponding eigenstates. The rule that connects overlap with probability is the Born rule. To calculate the probability of a particular outcome, one takes the overlap between the system's state and the eigenstate, and then squares its magnitude. This rule is not derived from deeper principles. It is a foundational postulate where the mathematical structure of the theory directly becomes experimental prediction. Once the probabilities are known, we can calculate average values. The expectation value of a quantity is the average result obtained when the same measurement is repeated many times on identically prepared systems. It is not the result of a single measurement. In any individual measurement, the system always returns a specific eigenvalue. Expectation values therefore describe the average behavior across many trials rather than a single event. Not all quantities can be known precisely at the same time. Two quantities are called compatible if there exists a state in which both have definite values. This occurs when their corresponding operators commute, meaning the order in which they act does not change the result. When operators do not commute, the corresponding quantities become incompatible. No state exists in which both can be simultaneously sharp. The most familiar example is position and momentum. The non-commutation of their operators leads directly to the uncertainty principle, a structural feature of the theory, rather than a limitation of measurement technology. Up to this point, the description assumes ideal measurements perfectly sharp and perfectly repeatable. In reality, experiments are often more complex. Measurements may be noisy, incomplete, or designed to gather only very weak information. To describe such situations, quantum mechanics extends into a broader framework known as generalized measurement theory. In this approach, measurements are described by more flexible sets of mathematical objects that still obey probabilistic rules, but do not necessarily lead to a single sharp outcome. This framework plays an important role in modern experiments and in the field of quantum information. Yet, regardless of how the details are refined, the core principles remain unchanged. Physical quantities correspond to operators. Measurement outcomes are their eigenvalues. Probabilities are determined by the Born rule. Expectation values describe averages over many measurements, and incompatibility arises from non-commuting operators. What makes this structure particularly powerful is its universality. The same mathematical principles can describe atoms, light, superconducting circuits, and even the quantum bits used in modern quantum computing systems. One striking feature of quantum mechanics is that its logical structure changes very little from one physical system to another. Whether the system involves atoms, photons, or superconducting circuits, the mathematical framework remains the same. Only the specific operators are modified to match the details of each system. At first, this way of thinking may feel unfamiliar. The familiar pictures of classical physics gradually give way to mathematical operations and abstract geometric relationships. Yet, it is precisely this level of abstraction that allows the theory to predict the behavior of nature with remarkable accuracy. One of the most famous concepts in quantum mechanics is the uncertainty principle. It is also one of the most frequently misunderstood. People sometimes assume that uncertainty is merely the result of imperfect measurements, or that measuring devices disturb the system too strongly. But that is not what the principle actually says. Even in a hypothetical world where every measuring device were perfectly precise, the uncertainty principle would still exist. It does not describe a limitation of experiments. It describes the structure of quantum states themselves. Certain physical quantities simply cannot be simultaneously sharp, not because our measurements are insufficient, but because such states do not exist in nature. This limitation is built directly into the mathematical structure of the theory. The most familiar example is position and momentum. Every quantum state possesses a certain spread in both of these quantities. When calculated precisely, the product of these two spreads is always bounded by a minimum value. No state can make this product smaller than that limit. This leads to an unavoidable trade-off. If a particle is localized very precisely in space, its state must contain many different momentum components. Conversely, if the momentum of a particle is well defined, the state must spread out across space. There is no shortcut that allows this trade-off to be avoided. Classical intuition often suggests that a particle must secretly possess both an exact position and an exact momentum, and that we simply do not know them yet. Quantum mechanics does not allow that assumption. The uncertainty principle is not about what is unknown. It is about what cannot simultaneously exist. The origin of this limit actually comes from a familiar mathematical fact. The description of a particle in position space and in momentum space are related through the Fourier transform. A function that is strongly localized in one representation must necessarily be spread out in the other. This is a general property of mathematics, not something unique to physics. Quantum mechanics adopts this structure and turns that mathematical trade-off into a physical limit. For this reason, the uncertainty principle is not an extra assumption added to the theory. It emerges naturally from the way quantum states are represented. A similar argument applies to any pair of quantities whose operators do not commute. The spin of a particle provides a clear illustration. For a particle with spin 1/2, measurements of spin along different directions correspond to different operators. These operators do not commute. If the spin is completely determined along one direction, a measurement along a perpendicular direction becomes entirely unpredictable. There is no state in which both values can be sharply defined at the same time. This has nothing to do with experimental error. It reflects the structure of the states that are allowed to exist. For that reason, the uncertainty principle does not say that the properties of a system are hidden somewhere waiting to be discovered. The quantum state itself does not contain definite values for incompatible quantities. Measurement does not reveal a number that was already there. It produces a result consistent with the structure of the state. This is the point where quantum mechanics departs most deeply from classical intuition. In classical physics, uncertainty simply reflects a lack of information. In quantum mechanics, for incompatible quantities, the theory itself does not permit sharp values to coexist. That does not mean the quantum world lacks precision. In fact, many modern technologies achieve extraordinary accuracy while operating entirely within the framework of the uncertainty principle. Atomic clocks, lasers, and quantum sensors are all examples. The principle only limits the simultaneous sharpness of certain quantities. It does not limit the overall precision of measurements. A single quantity can be determined with extremely high precision, provided one accepts that an incompatible quantity will become less well-defined. Modern quantum technologies even exploit this trade-off. Seen this way, the uncertainty principle is not a barrier. It is more like a map indicating what is possible and what is not. Between measurements, the quantum world is actually very orderly. The state of a system does not jump around or change randomly. Instead, it evolves smoothly according to a single rule known as the Schrödinger equation. This equation describes how the wave function changes with time when no measurement is taking place. If the state of the system at one moment is known and the Hamiltonian of the system is specified, then both its future and past states are completely determined. During this stage, there is no randomness. Randomness appears only when a measurement is performed. And it is the Hamiltonian that serves as the central mathematical object governing this continuous evolution. In quantum mechanics, the Hamiltonian plays a central role in governing the evolution of a system. It represents the total energy of the system, including both kinetic and potential energy. In classical mechanics, this quantity determines how a system moves through phase space. In the quantum picture, however, the Hamiltonian guides the motion of the wave function in a more abstract arena, Hilbert space. By changing the Hamiltonian, the entire way a system evolves in time changes as well, and this evolution follows the Schrödinger equation. One important feature of this evolution is unitarity. This property ensures that total probability is always conserved. Probability may shift from one region to another and may spread over time, but it never spontaneously appears or disappears. At the same time, unitary evolution is reversible. If the state of a system is known at one moment, the equations allow its past to be reconstructed just as easily as its future can be predicted. In the fundamental dynamics of the theory, there is no inherent arrow of time. Unitarity also preserves the geometric structure between states. The overlap between two quantum states does not change as they evolve. Two states that are initially completely distinct will remain distinct. States that partially overlap will also maintain the same degree of similarity. In geometric language, time evolution resembles a rotation in the space of states. The states are rearranged without being distorted. Among all possible states, there is a particularly simple class, the eigenstates of the Hamiltonian. For these states, the probability distribution does not change with time. The only thing that evolves is the phase of the wave function, which rotates steadily over time. But since observable quantities depend on the square of the wave function's magnitude, this rotating phase produces no measurable effect. For that reason, these states appear stationary. They are therefore called stationary states. However, most physical states are not energy eigenstates. Instead, they are superpositions of many different energy states. Each energy component evolves with its own phase. As time passes, these phases gradually shift relative to one another, producing continuously changing interference patterns. It is from these changing phase relationships that motion, oscillations, and transitions between energy levels arise. A clear illustration of quantum dynamics is the spreading of a wave packet. Initially, a wave packet may be prepared so that it is quite localized in space, resembling a particle located at a particular position. But such a localized state is not stable, because strong localization in space requires the presence of many different momentum components. Those components evolve at different rates. Over time, they separate from one another, and the wave packet begins to spread, even when no forces are acting. This reveals a fundamental feature of the quantum world. A particle is not a tiny object that naturally maintains a fixed shape. Localization in space is a fragile condition, often requiring interactions or confinement to maintain it. Left alone, a quantum state tends to spread. Yet throughout this entire process, the total probability remains conserved. Quantum mechanics describes this through the concept of probability flow. Probability density can move from one region to another. Much like the flow of a fluid, any change in one region is balanced by a flow entering or leaving it. Probability moves, but it never disappears. Up to this point, the picture is entirely orderly, continuous, deterministic, and reversible in time. But difficulties appear as soon as measurement enters the story. Measurement produces random outcomes and leaves behind records that cannot be reversed. Once a result has been recorded, the system does not return to its previous superposition state. This contrast leads to one of the deepest questions in quantum mechanics, the measurement problem. The Schrödinger equation appears to govern every physical system, yet the equation itself does not describe the appearance of a single definite outcome. If a measuring device is also treated as a quantum system and allowed to evolve according to the same rule, then the combined system, consisting of the object being measured and the measuring apparatus, will evolve into a superposition of all possible outcomes, each correlated with a different state of the device. And yet experience tells a different story. We always observe a single pointer position, a single number, a single outcome. The other possibilities predicted by the mathematics do not appear directly. This is not a minor technical detail. It represents a deep conceptual tension. Either the Schrödinger equation is incomplete, or the appearance of a single outcome must be explained in a way that remains consistent with the principle of superposition. Different interpretations of quantum mechanics offer different answers to this problem. But the important point here is not to choose which interpretation is correct. The important point is to recognize where the difficulty arises. Within the same theory, one set of rules describes continuous and reversible evolution. Another set describes sudden and irreversible measurement outcomes. Both are indispensable. This does not mean that quantum mechanics lacks precision. On the contrary, it is one of the most successful theories ever constructed. Its dynamics are continuous and deterministic. Its measurement outcomes are discrete and random. Holding both of these truths at once is the present state of the theory. Up to now, quantum states have been described using wave functions, which represent what are called pure states. When a system is completely isolated and its preparation is fully known, this description is sufficient in many real situations. However, things become more complicated. In such cases, a single wave function is no longer enough to describe the system, not because quantum mechanics fails, but because the information about the system is incomplete. Sometimes the uncertainty is purely classical. A system might be prepared in one state during some trials and in another state during others, without us knowing which occurred in a particular run. In other situations, the system may be entangled with another system. In that case, the combined system still has a well-defined quantum state. But if we examine only one part of it, a description in terms of a single wave function is no longer sufficient. When the quantum world is described using a wave function, the picture is often quite tidy, but reality is rarely that simple. Many situations arise in which a single wave function is no longer sufficient to capture the full state of a system. This is not because quantum mechanics reaches a limitation, but because the information about the system is no longer complete. To handle such cases, the theory uses a more general tool, the density matrix. The density matrix provides a complete description of a quantum state. It contains all the information needed to calculate measurement probabilities and expectation values, just like the wave function. But it also has the ability to describe situations that the wave function alone cannot: mix states and subsystems of larger systems. When a system is in a pure state, the density matrix can be constructed directly from the wave function. In that case, it is simply another way of organizing the same information. The physical content remains exactly the same, but when the state is mixed, its meaning changes. A mixed state describes a system that may be in one of several different pure states, each associated with a classical probability. The density matrix is then formed by combining the corresponding pure state matrices with appropriate weights. This combination reflects genuine uncertainty, rather than quantum superposition. A major advantage of this framework is that it treats pure states and mixed states within the same set of rules. Regardless of how the state arises, calculations of probabilities, averages, and time evolution are carried out in the same way. The difference lies only in how much information the state contains. A pure state corresponds to maximal knowledge about the system. A mixed state appears when some information is missing or inaccessible. This difference can even be quantified. One simple measure is the purity of the state. For a pure state, the purity equals 1. For a mixed state, it is less than 1. A deeper measure is quantum entropy. In quantum mechanics, the degree of mixedness is quantified by the von Neumann entropy. Pure states have zero entropy, while mixed states have positive entropy that increases as information becomes distributed or shared among entangled systems. The real power of the density matrix becomes clear when a physical system consists of multiple parts. In such systems, the state of the entire system may be perfectly known, while an observer has access to only one part of it. To describe that part alone, quantum mechanics uses an operation known as the partial trace. This operation removes the degrees of freedom that are not being observed and produces a reduced density matrix for the subsystem under consideration. Interestingly, even when the entire system is in a pure state, the reduced state of a subsystem can still become mixed. This happens when the different parts of the system are entangled with one another. In this case, the mixed nature of the subsystem does not reflect ignorance about the whole system. Instead, it reflects the fact that information has been distributed non-locally across different parts of the system. Here, we encounter one of the deepest insights of quantum mechanics. Entanglement can transform quantum correlations into classical-looking randomness when viewed locally. When part of an entangled system is ignored, the remaining part exhibits entropy and mixedness. For pure states of multipart systems, The amount of entanglement can even be measured by the entropy of the reduced state, a quantity known as entanglement entropy. The density matrix also clearly distinguishes between superposition and mixture. Two states may produce the same probability distribution for a particular measurement, yet still be fundamentally different. Superpositions contain phase relations that allow interference, while mixtures do not. In the density matrix, this difference appears in the off-diagonal elements. When these elements vanish, coherence and the possibility of interference disappear as well. For this reason, the process of decoherence can be understood very naturally in the language of density matrices. When a system interacts with its environment, entanglement spreads outward. If the environment is not monitored, taking the partial trace causes the state of the system to become mixed. Interference disappears, coherence fades, and classical behavior gradually emerges. There is no need to assume a sudden collapse of the state. Information has simply spread into degrees of freedom that are no longer being tracked. The density matrix also reflects the real conditions of physical experiments. No system is perfectly isolated. Noise and uncontrolled interactions are always present. With this formalism, such effects can be incorporated into the description without pretending that the system remains in a perfectly pure state. When a system is isolated, the density matrix evolves according to the same rule as the wave function in the Schrödinger equation. When environments or measurements are introduced, new effects appear: decoherence and the growth of entropy. It is precisely this ability to describe both situations within a single framework that makes the density matrix an indispensable tool in modern quantum mechanics. And in that picture, mixed states are not flaws of the theory, but a natural part of how the quantum world operates. In essence, mixed states are not a flaw or approximation of quantum mechanics. They are an essential part of how the theory describes uncertainty, subsystems, and especially the phenomenon of entanglement. The density matrix, therefore, does not replace the wave function. It extends the language of the theory, allowing it to describe situations in which information is incomplete, where the state of a system is shared among multiple parts, or dispersed into the environment, which is, in fact, the case for most real physical systems. But if quantum mechanics truly governs everything, from subatomic particles to the familiar objects around us, a natural question arises. Why does the everyday world appear so stable and classical? Why do ordinary objects have clear positions, solid shapes, and continuous histories in time? And why do we never observe a cup that is simultaneously sitting on a table and falling to the floor? An important part of the answer lies in the phenomenon known as decoherence. It does not resolve every conceptual difficulty in quantum mechanics, but without it, the emergence of the classical world would be very difficult to understand. The starting point of this story is quite simple. Macroscopic objects are almost never truly isolated. A tiny speck of dust, a chair, or a living body constantly interacts with its surroundings. Air molecules collide with their surfaces. Light scatters from every direction. Thermal radiation is emitted and absorbed. Countless weak interactions occur continuously, far too many to track individually. Each of these interactions creates entanglement between the object and its environment. Information about the state of the object begins to spread outward and becomes recorded in many different degrees of freedom of the environment. Because these details are not being tracked, the appropriate description of the object is no longer a pure quantum state. Instead, its state is represented by a reduced density matrix, obtained by tracing out the environmental degrees of freedom from the full description. As this process unfolds, a characteristic transformation appears. The off-diagonal elements of the density matrix, the elements that contain information about interference between different possibilities, rapidly decay in certain representations. What remains gradually takes the form of a classical probability distribution among different alternatives, rather than a coherent quantum superposition. This process is what we call decoherence. It does not depend on an observer, nor does it require an act of measurement or consciousness. It is purely a physical consequence of the system becoming entangled with its environment. And the larger the environment and the more interactions occur, the faster decoherence proceeds. Another important feature is that the environment does not suppress all states in the same way. During continuous interaction, certain states prove far more stable than others. These stable states are known as pointer states. Pointer states are the states that remain robust, even while the environment constantly monitors the system through microscopic interactions. For macroscopic objects, these states typically correspond to well-defined positions and orientations in space. An object located here rather than there leaves different traces in its environment. Light scatters differently. Air molecules bounce away along different trajectories. Thermal radiation carries away different patterns of information. These states are continually reinforced by the surrounding environment. By contrast, strange superpositions in which an object exists in multiple locations at once are extremely fragile. They are destroyed almost immediately by environmental interactions. This helps explain why classical physics focuses on quantities such as position and orientation. It is not simply because humans find them intuitive, but because the environment itself selects them as the most stable states. The timescales involved in this process are extraordinarily short. For macroscopic objects, decoherence occurs almost unimaginably quickly. A tiny dust particle in air can lose coherence between different position states in a time far shorter than any interval humans can perceive. By the time any observation could realistically be made, the quantum coherence has already disappeared. The situation is very different for microscopic systems. An electron in a high-quality vacuum, a photon trapped inside an optical cavity, or a superconducting circuit cooled close to absolute zero can maintain coherence long enough for quantum effects to be observed and even carefully controlled. At its core, mixed states are not a flaw or approximation of quantum mechanics. They are an essential part of how the theory describes uncertainty, subsystems, and especially entanglement. The density matrix, therefore, does not replace the wave function. Instead, it extends the language of the theory, allowing it to describe situations where information is incomplete, where the state of a system is shared among multiple parts, or dispersed into the environment conditions that actually occur in most real physical systems. But if quantum mechanics truly governs everything, from subatomic particles to the familiar objects around us, a natural question arises. Why does the everyday world appear so stable and classical? Why do ordinary objects have well-defined positions, solid shapes, and continuous histories in time? And why do we never see a cup that is simultaneously sitting on the table and falling to the floor? An important part of the answer lies in decoherence. It does not resolve every conceptual difficulty of quantum mechanics, but without it, the emergence of the classical world would be very difficult to understand. The starting point of this story is simple. Macroscopic objects are almost never truly isolated. A tiny dust particle, a chair, or a living organism constantly interacts with its environment. Air molecules collide with their surfaces. Light scatters in all directions. Thermal radiation is emitted and absorbed. Countless weak interactions occur continuously, far too many to track individually. Each of these interactions creates entanglement between the object and its environment. Information about the object's state begins to spread outward and becomes recorded in the many degrees of freedom of the environment. Because these details are not monitored, the appropriate description of the object is no longer a pure quantum state. Instead, its state is represented by a reduced density matrix, obtained by tracing out the environmental degrees of freedom from the full description. As this process unfolds, a characteristic transformation appears. The off-diagonal elements of the density matrix, the elements that contain information about interference between different possibilities, rapidly decay in certain representations. What remains gradually takes the form of a classical probability distribution among different alternatives, rather than a coherent quantum superposition. This process is called decoherence. It does not depend on observers, measurement acts, or consciousness. It is simply the physical consequence of a system becoming entangled with its environment. And the larger the environment and the more interactions occur, the faster decoherence takes place. Another important feature is that the environment does not suppress all states equally. During continuous interaction, some states prove far more stable than others. These stable states are called pointer states. Pointer states are those that remain robust even while the environment constantly monitors the system through microscopic interactions. For macroscopic objects, these states usually correspond to well-defined positions and orientations in space. An object located here rather than there leaves different traces in its environment. Light scatters differently. Air molecules bounce away along different trajectories. Thermal radiation carries away different patterns of information. These states are continuously reinforced by the surrounding environment. By contrast, strange superpositions in which an object exists in several positions at once are extremely fragile. They are destroyed almost immediately by environmental interactions. This helps explain why classical physics focuses on quantities such as position and orientation. It is not merely because humans are familiar with them, but because the environment itself selects them as the most stable states. The timescales involved in this process are astonishingly short. For macroscopic objects, decoherence occurs almost unimaginably quickly. A tiny dust particle in air can lose coherence between different position states in a time far shorter than any interval humans could perceive. By the time any observation could realistically be made, the quantum coherence has already vanished. The situation is very different for microscopic systems. An electron in a high-quality vacuum, a photon trapped in an optical cavity, or a superconducting circuit cooled close to absolute zero can preserve coherence long enough for quantum effects to be observed and even controlled. Much of modern experimental quantum physics is therefore devoted to a very specific goal, isolating physical systems as well as possible in order to slow down decoherence. Decoherence explains why interference between macroscopic possibilities is never observed. It shows why the surrounding world appears classical even though its underlying laws are fully quantum. When interactions with the environment are taken into account, classical probability is not something separate from quantum mechanics. It emerges naturally from the theory itself. However, it is important to recognize the limits of this explanation. Decoherence does not answer why we experience only a single outcome. After decoherence occurs, the mathematical description still contains multiple possibilities, each with its own probability. Decoherence prevents those possibilities from interfering with one another, but it does not select one outcome and eliminate the rest. That question lies at the heart of the measurement problem. Different interpretations of quantum mechanics offer different answers. Decoherence itself remains neutral. It does not support wave function collapse, nor does it assert a branching universe or hidden variables. Its strength lies precisely in this neutrality. Decoherence is not a philosophical layer added to the theory. It is a physical process that occurs regardless of how quantum mechanics is interpreted. Its real role is to act as a bridge. It connects the smooth, deterministic evolution of quantum states with the stable patterns of the classical world we observe. Through this bridge, the classical world is no longer an exception to quantum rules. It simply emerges naturally because physical systems constantly interact with their environments and are never truly isolated. Another feature of quantum mechanics pushes it even further from any classical theory: entanglement. Entanglement is not merely an ordinary correlation between systems, nor simply the result of missing information. It arises when multiple systems must be described together because none of them retains an independent quantum state of its own. In classical physics, no matter how strongly two objects interact, it is always possible in principle to assign each object a complete and independent description. In quantum mechanics, this is not always possible. Two systems are said to be entangled when their joint state cannot be written as the product of two individual states. The whole system exists as a single entity, while its parts no longer possess independent states in the familiar sense. This difference is important because entanglement produces correlations stronger than anything classical physics allows. These correlations persist even when the systems are separated by large distances, as long as the entangled state remains intact. It was precisely this feature that troubled some of the founders of quantum mechanics. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen presented a famous argument, now known as the EPR paradox. Their goal was not to reject quantum mechanics entirely, but to suggest that the theory might be incomplete. Their reasoning began with a simple scenario. Imagine two particles prepared in an entangled state and then separated far apart. By measuring one particle, an observer can predict with certainty the result of a corresponding measurement on the other particle, even though it is distant and not directly disturbed. Einstein, Podolsky, and Rosen argued that if a quantity can be predicted with certainty without disturbing the system, then it must correspond to an element of physical reality. They also assumed locality, meaning that physical influences cannot propagate faster than light. Combining these assumptions seemed to imply that the distant particle must already possess definite values before the measurement takes place. But quantum mechanics does not assign such predetermined values. According to the EPR argument, the theory therefore appeared incomplete. For decades, this issue remained largely philosophical. Quantum mechanics continued to work perfectly in experiments, yet the conceptual unease remained. Then in 1964, John Bell made a decisive advance. Bell showed that the assumptions behind the EPR argument were not merely philosophical, they could be tested experimentally. He proved that any theory reproducing the predictions of quantum mechanics, while preserving both locality and predetermined values, must satisfy certain statistical limits, now known as Bell inequalities. Quantum mechanics predicts that under suitable measurement conditions, entangled systems will violate these inequalities. Bell did not merely suggest this possibility. He calculated specific limits that local hidden variable theories could not exceed. A particularly practical version of these limits is known as the CHSH inequality. It involves measuring pairs of entangled particles with different settings on two sides and comparing the correlations between the outcomes. Beginning in the 1970s, experiments were designed to test these predictions, and they became increasingly sophisticated over time. The results have been clear. Bell inequalities are violated. The correlations predicted by quantum mechanics are indeed observed in laboratories. Modern experiments have even closed potential loopholes related to detector efficiency or the possibility of communication between measurement devices. The conclusion has become difficult to avoid. Nature does not obey both locality and predetermined values simultaneously. This does not mean that quantum mechanics allows faster-than-light communication. That is a common misunderstanding. Although entangled systems display correlations that cannot be explained by local mechanisms, they cannot be used to send instantaneous signals. Imagine two observers, often called Alice and Bob, sharing an entangled pair of particles. Each performs a measurement on their own particle. The outcomes that each observer sees locally are completely random. Alice cannot choose a measurement setting that controls the result Bob obtains. Bob's statistics do not depend on Alice's choices. Only when they later compare their results do the correlations become visible. This property is known as the no-signaling principle. Because of it, quantum mechanics remains compatible with special relativity. at least at the level of observable information transfer. The non-locality revealed by Bell's theorem is therefore subtle. It exists in the correlations between measurement outcomes, not in signals or causal influences that could transmit messages. Quantum mechanics is thus non-local in a very specific sense. The behavior of entangled systems cannot be reduced to independent local descriptions with predetermined properties. Yet, this does not imply a violation of relativistic causality. Entanglement also forces us to reconsider how physical properties are assigned to systems. In classical intuition, we often assume that physical quantities possess definite values whether or not they are measured. Quantum mechanics challenges this assumption, and Bell's theorem shows that it cannot be maintained in any simple local way. This challenge becomes even stronger with another foundational result, the Cauchy-Specker theorem. This theorem applies to quantum systems whose state space has 3 or more dimensions. It demonstrates that it is impossible to assign predetermined values to all observable quantities in a way that both agrees with quantum predictions and remains independent of measurement context. Here, context independence means that the value of a measurement does not change depending on which other compatible measurements are performed alongside it. Yet even this seemingly reasonable assumption cannot be maintained within quantum mechanics. Results such as the Cauchy-Specker theorem reveal something important. It is impossible to assign predetermined definite values to every physical quantity in a way that is independent of the measurement context. The outcome of a measurement is not simply the discovery of a number that already existed. It depends on the entire way the experiment is arranged. This idea is known as contextuality, and it lies deep within the structure of quantum mechanics. This means that the properties of a system are not merely uncovered by measurement. They are defined within a framework that includes how the measurement is performed. The context of the experiment becomes part of the physical description. When considered together, entanglement, the violation of Bell inequalities, and contextuality paint a consistent picture. Quantum mechanics does not describe a world made of independent parts, each carrying its own set of predetermined properties. Instead, it describes a world in which correlations play a fundamental role, where the whole can contain more structure than the sum of its parts, and where measurement outcomes cannot always be traced back to local events that existed beforehand. This does not make the theory chaotic. The rules of quantum mechanics remain precise and extremely well tested. Its strangeness does not lie in mere uncertainty, but in the structure of what the theory predicts. Entanglement is also not a phenomenon confined to thought experiments. In modern laboratories, it is created and measured routinely. It lies behind several emerging technologies, including quantum computing, quantum cryptography, and quantum teleportation. These technologies do not rely on sending information faster than light. Instead, they exploit the deep non-classical structure of quantum correlations. Perhaps the most important lesson of entanglement is a shift in how we understand the separateness of physical systems. Quantum mechanics does not merely modify our understanding of motion or energy. It reshapes how we understand independence between systems. Systems that appear separate may still share a single quantum description. What happens to one system can be correlated with another in ways that classical physics cannot explain, even though causality is never violated. This is not a weakness of the theory. On the contrary, it is one of the most precisely confirmed features of quantum mechanics, and it reminds us that intuitions formed from everyday experience are not always reliable guides to the deeper structure of reality. Quantum mechanics does not require us to abandon logic. It asks us to expand it. One fascinating aspect of quantum mechanics is that it works extraordinarily well in experiments. Yet its conceptual meaning remains debated. All interpretations of the theory agree on the mathematics and the experimental predictions. So far, no experiment has distinguished between them. And yet, physicists and philosophers continue to debate what the theory is truly saying about the world. From a purely pragmatic point of view, this might seem unnecessary. The equations work, The predictions are accurate. One can calculate atomic energy levels, scattering probabilities, or interference patterns without deciding what is really happening underneath. This attitude is sometimes summarized by the famous phrase, "Shut up and calculate." But for many people, that is not enough. Physics has never been only about prediction. It is also about understanding. Interpretations matter because they attempt to answer questions that the mathematical framework itself leaves open. What is a quantum state really? What does a measurement do to a system? Is randomness fundamental or only apparent? And what kind of world must exist for these rules to be true? Different interpretations offer different answers. The interpretation many people first encounter is often called the Copenhagen interpretation. Despite the clarity of the name, it is actually a rather loose collection of viewpoints associated with physicists such as Niels Bohr and Werner Heisenberg. Its central idea emphasizes the limits of description. Within this framework, quantum systems are described using classical concepts such as position, momentum, and measuring devices. But these concepts cannot be applied simultaneously in every situation. This idea is known as complementarity. Certain descriptions exclude others, not because of technical limitations, but because the concepts themselves become incompatible in the quantum domain. From this perspective, the wave function is not a picture of physical reality. It is simply a tool for predicting measurement outcomes. Asking what the system is doing between measurements is considered a misguided question. The theory only tells us what can be said about observations, not about a world existing independently of them. This approach avoids many paradoxes by refusing to push beyond what the theory explicitly describes. Its strength lies in its restraint. Yet for many people, that very restraint leaves the feeling that something important has been left unsaid. A very different approach was proposed by Hugh Everett in 1957. In what is commonly called the many worlds interpretation, the wave function is taken as a complete description of reality. It is not merely a computational tool, and it always follows the Schrödinger equation. There is no collapse of the wave function. When a measurement occurs, the measuring device and the observer become entangled with the system. All possible outcomes occur, each corresponding to a different branch of the wave function. From within any branch, an observer experiences only one result, because the branches no longer interfere with one another. But from the global perspective, the evolution of the state remains smooth and completely deterministic. This interpretation has a certain elegance. It removes the special role of measurement and applies the same rule to every physical process. However, it raises new questions. If every outcome occurs, why do probabilities follow the Born rule? What determines the boundary of a branch? And how should one understand the existence of countless worlds that cannot be directly observed? Another interpretation moves closer to classical intuition, Bohmian mechanics, also known as the pilot wave theory, adds additional structure beneath the standard formalism of quantum mechanics. In this view, particles always possess definite positions and follow precise trajectories. Their motion is guided by the wave function through a specific guiding equation. The wave function still evolves according to the Schrödinger equation, but it is no longer the entire description of the system. A complete description includes both the wave function and the actual positions of the particles. Measurement outcomes are determined by these positions, while randomness arises because the initial positions cannot be known exactly in practice. Bohmian mechanics reproduces all predictions of non-relativistic quantum mechanics, but it accepts an important consequence. The guiding equation is explicitly non-local. The motion of one particle can depend instantaneously on the configuration of particles far away. Extending the theory to relativistic quantum field theories is possible but introduces both technical and conceptual challenges. Nevertheless, this approach demonstrates that quantum phenomena do not necessarily require fundamental randomness. What appears unavoidable instead is non-locality. Some interpretations go further by modifying the theory itself. Collapse models propose that the Schrödinger equation is not completely exact. It must be supplemented with a random process that causes the wave function to spontaneously localize. One well-known example is the GRW model. In this framework, an individual particle experiences collapse only very rarely. But for macroscopic objects containing enormous numbers of particles, collapse events occur constantly, rapidly forcing the wave function into localized states. These models have an obvious advantage. They directly solve the measurement problem by ensuring that only a single outcome occurs. They also make predictions slightly different from standard quantum mechanics, meaning they could in principle be tested experimentally. However, the collapse mechanism is often viewed as somewhat arbitrary, since it introduces new parameters whose physical origin is not fully clear. Other interpretations shift the focus toward the concept of relations itself. Relational quantum mechanics proposes that the properties of a system exist only relative to other systems. There is no absolute state of the universe independent of observers. What counts as real depends on the relationships between systems rather than a single global description. The consistent histories approach moves in another direction. Instead of focusing on individual measurements, it assigns probabilities to entire sequences of events, called histories, but only sets of histories that satisfy certain consistency conditions are allowed, preventing interference between different possibilities. Finally, some views push subjectivity even further. In cubism, or quantum Bayesianism, the wave function is not considered a description of the world itself. It represents an agent's personal beliefs about the experiences they may encounter in the future. From this perspective, quantum mechanics does not directly describe external reality, but rather how an observer updates their expectations when interacting with the world. In this view, the outcomes of measurements are real experiences that occur, but the probabilities attached to them are interpreted as degrees of belief held by the observer, updated according to rules similar to Bayesian inference. Under this interpretation, quantum mechanics is no longer seen as a direct description of an objective external world. Instead, it becomes a tool that helps an agent make decisions based on expectations about future experiences. Each interpretation of quantum mechanics emphasizes different aspects of the theory. Some retain determinism but accept non-locality. Others attempt to preserve locality by abandoning the idea that properties exist prior to measurement. Some modify the very dynamics of the theory. Others deny that the wave function represents an objective entity at all. Yet, despite these differences, all interpretations agree on experimental predictions. Right. So far, no experiment has been able to distinguish between them. This situation is both a strength and a source of confusion. It shows how remarkably consistent and robust quantum mechanics is, but at the same time, the deepest questions about what the theory truly says about reality remain open. In the history of physics, this is not unprecedented. Debates about the nature of space, time, and gravity also continued long after the equations themselves were well understood. Only when new experiments or new theoretical ideas appeared did the broader picture begin to change. At present, interpretations function as conceptual lenses. They shape how people think about quantum mechanics, how it is taught, and how scientists attempt to extend it. They influence intuition even when they do not change the results of calculations. It remains unclear whether these interpretations reflect deeper structures of the universe or simply represent different ways of organizing information. But one thing is clear: quantum mechanics forces us to separate prediction from explanation. The theory tells us with unprecedented precision what will happen when an experiment is performed, but it does not provide a single answer about how to imagine the world producing those outcomes. Perhaps this tension is not a flaw, but a clue. One place where quantum mechanics departs most dramatically from everyday intuition is spin. Spin is a form of angular momentum that particles possess intrinsically. It does not arise from actual rotation in space and cannot be understood by imagining a tiny object spinning like a top. An electron, for example, has a spin of 1/2. This number is not a rotation speed, a size, or a frequency. It is simply a label describing how the electron responds when rotated in space and when placed in a magnetic field. If one tries to imagine spin as a literal physical rotation, contradictions appear almost immediately. If an electron were a tiny rotating sphere, its surface would have to move faster than light. Nature does not behave that way. Spin is a purely quantum property. This property was revealed dramatically in the Stern-Gerlach experiment. A beam of silver atoms is sent through a magnetic field whose strength varies with position. According to classical intuition, the magnetic moments of the atoms should point in many directions, causing the beam to spread into a continuous band on the detection screen. But that is not what happens. Instead, the beam splits into two distinct branches. Not many different deflections, just two. This result shows that the angular momentum associated with the atoms is quantized. When measured along a particular direction, it can only take specific values. Spin is not a hidden classical variable. It is fundamentally discrete. Behind this discreteness lies a powerful mathematical structure. In quantum mechanics, angular momentum is described by operators that obey special relationships known as commutation relations. In words, the essential relation states that the commutator of the x component of angular momentum with the y component equals I times the z component, and analogous relations hold when the axes are permuted. These relations are not arbitrary assumptions. They arise directly from the rotational symmetry of space. From this structure, a remarkable result emerges. Angular momentum cannot take arbitrary values. Its possible values occur in discrete levels labeled by a number called J. This number can take values such as 0, Arfenji, Arfenjasan, and so on. No values exist in between. Nature simply skips them. Among these possibilities, spin, 1, 2 systems are the simplest, but still deeply non-trivial. Electrons, protons, and many other fundamental particles belong to this class. The quantum state of a spin, 1-2 system lives in a two-dimensional space. When spin is measured along any axis, only two outcomes are possible. These outcomes are usually called up and down, but these labels should not be taken literally. They are simply names for two possible measurement results, not tiny arrows actually pointing in space. If the same particle is measured along a different direction, such as a horizontal axis, the outcomes again appear as two possibilities, but these correspond to different combinations of the original states. What makes spin particularly interesting is that a state definite along one axis is generally not definite along another axis. A particle that is certainly up along the vertical direction will produce completely unpredictable results if measured along a perpendicular direction. This is another manifestation of incompatible observables and non-commuting operators. Mathematically, the spin operators of a spin 1-2 system can be represented by simple matrices known as the Pauli matrices. These matrices capture the entire algebraic structure of spin and make calculations straightforward. Physically, they describe how the state responds to measurements and to magnetic fields. Because a spin 1-2 system has only two distinct states, it forms the basis of many modern quantum technologies. In quantum information science, such a system is called a qubit, unlike a classical bit, which can be either 0 or 1. A qubit can exist in a superposition of both states, with physically meaningful phases. This ability lies at the heart of quantum computation and quantum communication. To visualize the state of a spin 1-2 system, physicists often use a geometric picture known as the Bloch sphere. In this representation, every pure state corresponds to a point on the surface of a sphere. One pole of the sphere represents the spin-up state along a chosen axis, usually the vertical axis. The opposite pole represents spin-down. Points along the equator correspond to equal superpositions of the two states that differ only in their relative phase. Every pure state lies somewhere on the surface of the sphere. And this picture is more than just a metaphor, it reflects the true structure of the theory. Any unitary evolution of a spin 1-2 system corresponds to a rotation of the Bloch sphere. For example, when the system is placed in a magnetic field, the state vector moves smoothly across the sphere's surface, tracing a trajectory that reflects the system's dynamics. Mixed states also have a place in this picture. Instead of lying on the surface, they appear inside the sphere. The closer a point is to the center, the more mixed the state becomes. The center itself represents a completely random state in which all measurement outcomes occur with equal probability and coherence has vanished. The Bloch sphere is one of the rare cases in quantum mechanics where an abstract mathematical structure can be represented by an intuitive geometric image without sacrificing precision. It clearly shows how superposition, phase, measurement, and dynamics are connected within a unified structure. Spin also highlights an important lesson about measurement. When spin is measured along a given axis, we are not discovering a vector that already existed in space. We are producing a result consistent with the quantum state and the measurement context. Changing the measurement axis means asking a different question of the same system. This contextual nature is not a flaw of the theory. It is a fundamental feature, reflecting the deep relationship between symmetry, measurement, and information in quantum mechanics. Spin does not describe hidden mechanical rotation. It describes how quantum systems respond when they are probed. From the structure of atoms to magnetic resonance imaging, from particle physics to quantum computers, spin plays a central role. Its algebra determines transition rules, its quantization helps stabilize matter, and its two-level structure opens the door to entirely new technologies. Yet spin quietly retains its abstract character. It does not evoke familiar mechanical pictures. It is not easily visualized as motion. It simply follows its rules with remarkable consistency. Spin reminds us that quantum mechanics does not always replace classical ideas with more complicated versions of the same concepts. Sometimes it replaces them with entirely different concepts. Angular momentum that exists without physical rotation is one such example. To understand spin is to accept that not every property requires a classical picture in order to be real. Some properties exist simply because the mathematical structure allows them, and because experiments compel us to acknowledge them. In the quantum world, that is enough. One of the quiet strengths of quantum mechanics lies in the way it ties structure to behavior. Many patterns in physics are not accidental. They are enforced by symmetry. And whenever a symmetry appears, another consequence almost always follows. Something is conserved. This connection was first clarified in classical physics by M. E. Noether, but it carries over naturally into quantum mechanics. The idea can be stated briefly. Even though its consequences are far-reaching, every continuous symmetry of a system corresponds to a conserved quantity. In quantum mechanics, this relationship becomes especially clear. If an observable commutes with the Hamiltonian, then its expectation value does not change with time. In other words, that quantity is conserved during the evolution of the system. This rule is not an extra assumption added afterward. It follows directly from the structure of time evolution itself. There is another way to view the same relationship. Observables do not merely represent quantities that can be measured. They also generate transformations. Momentum generates translations in space. Angular momentum generates rotations. Energy generates evolution in time. The operators associated with conserved quantities are precisely the generators of the corresponding symmetries. This dual role is one reason quantum mechanics initially appears abstract. The same mathematical object both describes something measurable and determines how a state changes under a symmetry transformation. Consider spatial translation symmetry. Imagine a system in which the laws of physics are the same everywhere. No location is preferred. This property is called translational invariance. If the Hamiltonian does not depend explicitly on position, the system possesses this symmetry. In that case, momentum is conserved. In such a system, the average momentum of a particle does not change with time unless something breaks the symmetry, such as an external force or a physical boundary. At the same time, momentum acts as the generator of translations. When the appropriate transformation is applied to a wave function, the entire wave function shifts in space. Specifically, applying the exponential of I times the momentum operator, multiplied by the displacement and divided by, shifts the wave function by exactly that distance. Its shape remains unchanged. Only its position moves. This is not a metaphor. It is a precise mathematical statement. The operation that defines momentum is exactly the operation that produces translations in space. Conservation of momentum and the uniformity of space are therefore two sides of the same structure. Rotational symmetry works in the same way. If a system looks identical after being rotated, it has rotational symmetry. When the Hamiltonian remains unchanged under rotations, angular momentum is conserved. This is especially clear in systems with central forces, where the interaction depends only on the distance from a center and not on direction. The hydrogen atom is a classic example. The electrostatic force between the proton and electron depends only on the distance between them, not on the orientation of the atom in space. As a result, angular momentum is conserved. Angular momentum operators act as the generators of rotations. When the appropriate rotation operator is applied to a quantum state, the result is a new state corresponding to the original one rotated in space. The algebra of angular momentum operators mirrors the mathematical structure of continuous rotations in three-dimensional space. This is not a coincidence. It is the mathematical expression of rotational symmetry. Because rotations can occur around different axes, the components of angular momentum do not commute with one another. This is not a flaw of the theory. It reflects the geometry of space itself. Rotations around different axes also do not commute. Performing two rotations in different orders generally produces different results. Energy fits into the same structure. Symmetry under translations in time corresponds to the conservation of energy. If the Hamiltonian does not depend explicitly on time, the energy of the system remains constant. Energy acts as the generator of time evolution. Just as momentum generates spatial translations, these ideas may sound abstract, but their consequences are extremely concrete. One of the most important is the existence of selection rules. Selection rules determine which transitions between states are allowed and which are forbidden. They do not require detailed calculations of forces or trajectories. They follow directly from symmetry. When a system undergoes a transition, for example, when an atom emits or absorbs light, the probability of that process depends on a quantity known as a matrix element. This quantity involves the overlap between the initial state, the final state, and the operator responsible for the interaction. If a transition violates a conservation law imposed by symmetry, the corresponding matrix element becomes exactly zero. Not small, not unlikely, exactly zero. The transition simply cannot occur. This is why only certain lines appear in atomic spectra. It also explains why light emitted by atoms has specific frequencies and polarization states. Many processes are completely forbidden, regardless of how much energy the system might have. In atomic physics, electromagnetic transitions provide a clear example. The interaction between light and matter respects rotational symmetry and certain spatial reflection symmetries. As a result, the angular momentum of an atom cannot change arbitrarily when emitting or absorbing a photon. For electric dipole transitions, which are the most common, the total angular momentum of the atom can change by at most 1 unit. Transitions requiring larger changes are forbidden. There is also a quantity known as parity. In these transitions, parity must change. Signed states that are symmetric under spatial inversion can only transition to antisymmetric states, and vice versa. These rules are not accidental patterns in experimental data. They arise directly from the symmetries of the electromagnetic field and from how that field interacts with charged particles. Once the symmetries are known, the selection rules follow. Symmetry also explains another familiar phenomenon, energy degeneracy. This occurs when several different quantum states share the same energy level. When a system has symmetry, states related by that symmetry must have identical energies. In a system with rotational symmetry, states with the same total angular momentum but different orientations have the same energy. When a symmetry is broken, this degeneracy disappears. If a system is placed in an external magnetic field, rotational symmetry is reduced and the energy levels split. This phenomenon is known as the Zeeman effect. The effect is not mysterious. It is simply symmetry breaking becoming visible. For this reason, symmetry has become one of the most powerful tools in physics. It allows firm conclusions to be drawn even when the detailed dynamics of a system are not yet fully known. It is not necessary to solve the full equations of motion to know that momentum is conserved in free space, or that certain transitions in atoms are absolutely forbidden. Symmetry alone is enough to tell us that. Quantum mechanics pushes this idea even further by placing symmetry at the center of its formal structure. Operators generate transformations, commutation relations encode geometry, and conservation laws emerge as statements about what remains unchanged as a state evolves in time. This perspective also clarifies why, in some measurements, conservation laws appear to be violated. When a system interacts with a measuring device or with its environment, the symmetry of the subsystem alone may no longer hold. Even though the symmetry of the total system remains intact, momentum might not appear conserved if we look only at a particle, but it remains conserved if the particle and the measuring apparatus are considered together. To keep the physical bookkeeping correct, everything that actually participates must be included in the description. Seen this way, conservation laws no longer look like fragile rules that observation can somehow break. They are global constraints that apply to closed systems. Apparent violations are usually signs that something has been left out of the description. Thinking in terms of symmetry also opens the door to deeper ideas in modern physics. Gauge symmetries, internal symmetries, and space-time symmetries all play central roles in how we describe nature. Quantum mechanics provides the language in which these structures can be expressed consistently. At a deeper level, symmetry also tells us which questions are meaningful in the first place. It restricts the forms that physical laws can take. It determines what may change and what must remain fixed. In a theory where measurement outcomes appear only as probabilities, symmetry becomes one of the few sources of certainty. When symmetry exists, something is protected. A quantity cannot drift arbitrarily. A transition cannot occur. A pattern must repeat. That is why symmetry is not merely aesthetic elegance. It is structural constraint. It shapes the space of possibilities even before any detailed calculations begin. In quantum mechanics, this becomes especially clear, because the theory does not begin with forces and trajectories, as classical physics does. It begins with states and transformations. Symmetry tells us which transformations matter and which quantities remain unchanged under them. Once this is recognized, conservation laws no longer seem like separate principles imposed on nature. They appear almost inevitable direct consequences of the ways nature allows itself to change while preserving its identity, quietly. This is one of the deepest lessons that quantum mechanics offers. From here, quantum information emerges as a shift in perspective. It does not treat the strange features of quantum mechanics as side effects. Instead, it treats them as resources, rather than asking only what a system is doing. It asks what kind of information the system can carry, how that information can be transformed, and what the laws of physics allow or forbid. At the center of this approach is the qubit. A qubit is the quantum version of the classical bit. Like a classical bit, it has two distinguishable states. But unlike a classical bit, it is not forced to be entirely in one state or the other. It can exist in a superposition of both, with a relative phase that has genuine physical meaning. This difference is not merely philosophical. It leads to very concrete consequences. A qubit can interfere with itself. Multiple qubits can become entangled, forming joint states that cannot be separated into independent parts. These properties create the distinctive power of quantum information and also its fragility. One of the earliest surprising results in this field is the no-cloning theorem. Its statement is remarkably strong. It is impossible to create a perfect copy of an unknown quantum state. This is not a limitation of technology, nor a consequence of experimental noise. It is a mathematical impossibility built directly into the structure of quantum mechanics. The reason is subtle. To copy a state, there would need to exist a physical process capable of taking any unknown input state and producing two identical outputs, regardless of what the input is. But such a process would have to preserve inner products between states. And quantum mechanics does not allow this universally. Any attempt to clone a state will either disturb it or fail to reproduce it exactly. This limitation has profound implications. Quantum information cannot be backed up in the way classical information can. There is no perfect quantum photocopier. Yet this very restriction opens the door to a new kind of security. An eavesdropper cannot intercept and copy quantum information without leaving traces. Any attempt to extract information inevitably disturbs the state. This idea lies at the heart of quantum cryptography. Before reaching that point, two protocols illustrate how dramatically entanglement can reshape communication. One of them is quantum teleportation. Despite its science fiction name, no object is transported, and nothing travels faster than light. What is transferred is a quantum state. In this protocol, two parties traditionally called Alice and Bob begin by sharing an entangled pair of qubits. Alice also holds a third qubit in an unknown state, which she wishes to transfer to Bob. By performing a joint measurement on the two qubits in her possession and sending the result through an ordinary classical channel, Alice allows Bob to reconstruct the original state on his qubit. The original state does not survive the process. It is destroyed the moment Alice performs her measurement. No second copy is created. The entire procedure works only because of two ingredients together: pre-shared entanglement and classical communication. Without either one, the protocol fails. Quantum teleportation does not violate causality and does not allow faster-than-light communication. It fully respects the limits imposed by relativity. Another protocol works almost in the opposite direction. It is known as superdense coding. Here again, Alice and Bob begin with a shared entangled pair. Alice performs one of several possible operations on her qubit and then sends that qubit to Bob. When Bob measures the two qubits together, he can extract more classical information than a single qubit could normally carry. More precisely, the qubit Alice sends can convey two classical bits, provided the entanglement was prepared in advance. This does not violate any physical limit, because the entanglement itself is a resource that was established beforehand. The protocol simply shows that quantum correlations allow information to be compressed and utilized more efficiently than classical correlations. These examples reveal something deeper, the promise of quantum computing. A quantum computer processes information using qubits, quantum gates, and finally measurements. A computation proceeds by preparing an initial state, manipulating it through a carefully controlled sequence of operations, and then measuring to extract the result. The power of this type of computation does not come from trying all answers at once. Although that phrase is often used, it is appealing but misleading. The real power comes from interference. A quantum algorithm is designed so that unwanted computational paths cancel each other out, while the correct paths reinforce one another. By the time the final measurement occurs, the probability of obtaining the correct answer has become very large. One of the most famous examples is Shor's algorithm, which can factor large numbers exponentially faster than the best-known classical algorithms. Because factoring underlies many widely used cryptographic systems, this result shows that, in principle, a sufficiently powerful quantum computer could break them. Another example is Grover's algorithm, which searches an unsorted database faster than any classical method by a quadratic factor. The speed-up is not exponential, but it is provably optimal. No quantum algorithm can do better for that problem. These algorithms do not work through some vague notion of parallelism. They rely on extremely precise control of amplitudes and phases. They succeed only when coherence is preserved and interference is carefully orchestrated. For this reason, quantum computation is extraordinarily sensitive to noise. Real qubits are never perfectly isolated. They inevitably interact with their surroundings. Decoherence and operational errors rapidly degrade quantum information. If left unchecked, these errors quickly overwhelm any computation. This is where quantum error correction appears as the only viable path forward. At first glance, the idea seems impossible. How can errors be corrected when quantum states cannot be copied? And when measurement itself disturbs the very information one wants to protect? The answer lies in an idea that is both subtle and remarkably ingenious. Instead of placing all the information in a single physical qubit, quantum error correction spreads that information across many qubits through entanglement. The logical information is not stored in any single local location. Instead, it is encoded non-locally throughout the entire system. Because of this structure, it becomes possible to perform special measurements known as syndrome measurements. These measurements detect the presence and type of errors without revealing the quantum information itself. Once an error is detected, appropriate corrective operations can be applied to restore the desired state. This process can be repeated continuously, allowing quantum information to remain stable even while the system exists in a noisy environment. One of the most prominent approaches today is the surface code. In this method, qubits are arranged in a two-dimensional lattice, and logical information is encoded in the global properties of the system rather than in local details. To cause a serious logical error, many small errors would need to accumulate along extended paths across the lattice. This feature makes the code remarkably robust. The protection is often described as topological, because it depends on the global structure of the system rather than on small local fluctuations. These ideas return to the domain of communication in quantum cryptography. One of the earliest and simplest protocols is BB84. In this protocol, Alice sends qubits to Bob, each prepared in a measurement basis chosen at random. Bob also measures them using randomly chosen bases. Afterwards, the two parties publicly compare which bases they used and keep only the cases where their choices matched. If an eavesdropper attempts to intercept and copy the qubits, the no-cloning theorem ensures that disturbances will appear. These disturbances can be detected statistically. The crucial point is that the security of the protocol does not rely on the difficulty of solving some computational problem. It relies directly on the laws of physics. More advanced approaches go even further. In device-independent quantum key distribution, one does not even need to trust the internal workings of the devices being used. Security is certified by observing violations of Bell inequalities. If the measured correlations are strong enough, then no eavesdropper, no matter how powerful, can interfere without being detected. This leads to a remarkable idea: security guaranteed not by secrecy or complexity, but by the structure of reality itself. Quantum information theory has reshaped the way quantum mechanics is understood. It treats entanglement as a usable resource. It reinterprets uncertainty and measurement as limits on the flow of information. It connects abstract principles with concrete operational tasks. Its influence has also spread into other areas of physics. Concepts such as entanglement, entropy, now play central roles in condensed matter physics, quantum field theory, and even approaches to quantum gravity. Information has become a unifying language. At the same time, quantum information theory also clarifies certain fundamental limits. Perfect cloning is impossible. Faster-than-light signaling is forbidden. Complete isolation does not exist. These are not technical inconveniences. They are the rules of nature. Quantum computers are difficult to build, not because the ideas are vague, but because nature is demanding. Coherence must be preserved. Errors must be controlled. Every operation must be precise. Progress is being made, but slowly and with considerable effort. Whether large-scale quantum computers will ultimately transform computation remains an open question. What has become clear, however, is that quantum information has changed how quantum mechanics itself is viewed. It shows that the theory is not only about particles and waves, it is also about information. In that sense, quantum information does not add anything fundamentally new to quantum mechanics. It simply reveals something that was already there, waiting to be recognized. In practice, no quantum system exists in perfect isolation. Even the most carefully controlled experiments take place within an environment, and that environment is never completely quiet. Stray electromagnetic fields, thermal radiation, mechanical vibrations, surrounding particles, and internal degrees of freedom of the system all contribute influences. These interactions may be weak or strong, fast or slow, but they are always present. Once a system interacts with its environment, its behavior changes in systematic ways. The phase relationships between components of the quantum state gradually degrade, a process known as decoherence. Energy may leak into or out of the system, a phenomenon called dissipation. After sufficient time, the system may approach a thermal equilibrium determined by the surrounding environment. These effects are not random accidents. They are inevitable consequences of coupling to external degrees of freedom. To describe such situations, a simple wave function is no longer sufficient. The appropriate language is the density matrix, which allows both quantum coherence and statistical uncertainty to be tracked simultaneously. For open systems, the density matrix no longer evolves according to the simple reversible Schrödinger equation. Instead, its evolution reflects both the system's internal dynamics and the continual influence of the environment. In many physically important situations, the environment behaves almost memorylessly. Each interaction affects the system, but the environment does not retain detailed information to feed back later. This regime is known as Markovian. When this approximation holds, the evolution of the density matrix is described by a special type of equation known as the Lindblad equation. The Lindblad equation is a master equation. It describes the rate of change of the density matrix as the sum of two parts. One part is the familiar Hamiltonian term, representing the unitary and reversible evolution of the system. The other part consists of additional terms describing the influence of the environment. These terms contain operators, often called jump operators, Each operator represents a way in which the system can exchange energy or information with the environment. Some jumps correspond to energy loss, for example, when a photon is emitted. Others describe dephasing, in which relative phases become randomized while the system's energy remains unchanged. The specific form of these operators depends on the physical nature of the interaction between the system and its environment. What makes the Lindblad equation especially important is not only what it describes, but what it guarantees. Its structure ensures that the density matrix always remains physically valid. Probabilities remain positive. The total probability always sums to 1. No unphysical states are produced. This consistency does not arise automatically. It requires a very specific mathematical structure. And the Lindblad equation represents the most general form of evolution that satisfies these conditions under the Markovian assumption. Because of this, it has become an extremely powerful and widely used framework. It underlies theoretical descriptions of atomic decay, laser cooling, superconducting circuits, quantum optics, and many other systems where environmental influence cannot be ignored but can still be controlled. However, the Lindblad equation describes only average behavior. It tells us how the density matrix evolves when we repeat an experiment many times and average over all runs. It does not directly describe what happens in a single experimental realization, especially when the environment is being continuously monitored. To understand individual experimental records, a different viewpoint is needed. That viewpoint is provided by quantum trajectory methods. Imagine an open quantum system coupled to an environment that is being observed, for example, through photon detectors. In each experimental run, the environment produces a particular sequence of detection events, or possibly no events at all, conditioned on that sequence of observations. The state of the system evolves in a way that is both continuous and punctuated by sudden changes. Quantum trajectory methods describe exactly this process. Instead of a smooth equation for the density matrix, the system follows a stochastic trajectory. Most of the time it evolves continuously under an effective non-Hermitian Hamiltonian. Occasionally, a quantum jump occurs, corresponding to an interaction detected in the environment. Each jump abruptly changes the state. Each individual trajectory corresponds to one possible history of the system, conditioned on what has been observed in the environment. Different experimental runs produce different trajectories. When one averages over all of them, the result reproduces precisely the Lindblad equation for the density matrix. In this sense, the master equation appears as the statistical average of many possible underlying quantum histories. There is a perspective that makes the dynamics of open quantum systems much clearer. When we continuously observe the environment surrounding a quantum system, randomness does not appear as some vague source of noise. It arises from something simpler. We only know part of the information. The environment is constantly and quietly recording the state of the system. Whenever we monitor that environment, the leaked information becomes a concrete record, forcing the system's state to update accordingly. Within this picture, the concept of a quantum trajectory emerges. At first, it may seem like a mathematical trick, but in the laboratory, it appears quite directly. In quantum optics experiments, individual emitted photons can be tracked. In superconducting circuits, microwave signals leaking from resonators are measured in real time. What researchers observe on their detectors closely matches the picture described by quantum trajectories. Looking at open quantum systems also clarifies two processes that are often confused: decoherence and dissipation. A system can lose phase coherence simply because information about its state leaks into the environment even when almost no energy is exchanged. That is decoherence. Dissipation is different. It directly involves the flow of energy. The two processes may occur together, but conceptually they are distinct and often unfold on different timescales. If the environment is large enough, and maintained at a fixed temperature. Another layer of dynamics appears: thermalization. As the system repeatedly interacts with countless degrees of freedom in the environment, it gradually relaxes toward a thermal state. In theoretical descriptions, this process is expressed through jump operators and their associated transition rates. What is remarkable is that this approach to equilibrium does not need to be imposed externally. It emerges naturally from the sequence of interactions with the environment. Open quantum systems therefore lie at the boundary between two worlds. Decoherence explains why interference patterns disappear. Dissipation explains why energy gradually relaxes. And continuous monitoring explains how classical records arise from quantum processes. From this perspective, classical behavior is not something added later. It emerges naturally when a quantum system is no longer perfectly isolated. Yet the story does not end with loss. As the theory of open systems developed, physicists realized that the environment is not only destructive. If carefully engineered, it can do the opposite. Certain forms of controlled dissipation can stabilize entanglement or drive a system toward desired states. In that case, the environment becomes a tool. This shift in thinking has changed how quantum experiments are designed. Instead of attempting to eliminate every interaction, researchers increasingly control them. Noise is characterized, couplings are engineered, and decoherence is managed rather than merely suppressed. From this perspective, quantum mechanics has never really been a theory of isolated objects floating in a vacuum. From the beginning, it has been a theory of interaction, probability, and information. When the environment is included explicitly, the theory does not weaken, it becomes richer. The loss of coherence, the flow of energy, and the emergence of classical behavior are not failures of quantum mechanics. On the contrary, they are among its most successful explanations. Understanding open systems does not make the quantum world less strange. It simply makes the picture more complete. One of the fields where this picture becomes especially clear is quantum optics, the study of light as a quantum system. In classical physics, the electromagnetic field is described as a continuous wave spreading through space. But when the full process of quantization is applied, this picture changes profoundly. In quantum theory, the electromagnetic field is not a collection of tiny light particles flying through space in the usual sense. Instead, it is a field whose excitations are discrete. These excitations are what we call photons. A photon is not a little marble made of light. It is a discrete packet of energy associated with a specific mode of the electromagnetic field. Each mode, defined by a particular frequency and spatial structure, behaves mathematically just like a quantum harmonic oscillator. One of the most elegant results of quantizing the electromagnetic field is this: each mode of the field carries discrete energy levels, just like a mass attached to a spring in quantum mechanics. These energy levels are evenly spaced, and the number of excitations present in a mode is called the photon number. When that number is 0, the mode is said to be in its vacuum state. But vacuum here does not mean absolute emptiness. Even when no photons are present, the state still contains well-defined quantum fluctuations. This fluctuating background helps explain why light sometimes behaves like a wave and sometimes like a particle. When many photon states combine coherently, light displays wave-like behavior. But when energy is exchanged in discrete amounts, its particle nature becomes evident. Among the many quantum states that light can occupy, there is a special class that comes closest to classical intuition. These are called coherent states. A well-stabilized laser produces light that is very close to such a state. In a coherent state, the electromagnetic field carries a well-defined phase, and its oscillations, when averaged, follow the same equations that describe classical electromagnetic waves. Interestingly, the number of photons in such a state is not fixed. Instead, it fluctuates according to a Poisson distribution. This means the photon number varies, but in a very specific statistical way. When the average photon number becomes large, the relative fluctuations become very small. That is why a strong laser beam appears so stable that it almost looks classical. Even so, calling coherent states the most classical states of light must be understood carefully. They are still fully quantum states. They still carry quantum noise, and they remain constrained by uncertainty relations. Their special property is simply that these uncertainties are balanced in such a way that the system's behavior mimics the classical world as closely as quantum mechanics allows. Quantum optics becomes especially fascinating when light is prepared in states that have no classical counterpart. These are called non-classical states of light. Familiar examples include single photon states, squeeze states, and entangled photon pairs. A single photon state, as the name suggests, contains exactly one excitation in a particular mode of the field. Such a state cannot be described as a wave with random amplitude fluctuations. It is fundamentally discrete. When measured, its energy appears as a single event that cannot be subdivided. A powerful way to recognize the non-classical nature of light is to examine photon statistics. Classical light sources tend to emit photons in clusters, a phenomenon known as bunching. But with a single photon source, the opposite occurs: anti-bunching. Once a photon is detected, the probability of detecting another immediately afterward is strongly suppressed. No classical wave model can account for this behavior. An even more striking effect appears when two identical photons enter a beam splitter from two different input ports at exactly the same time. Classical intuition suggests that each photon would randomly choose an output port. Quantum reality is very different. The two photons always leave together through the same port. They never separate. This phenomenon, the Hongo-Mandel effect, arises from quantum interference between indistinguishable processes. The effect provides a direct test of photon indistinguishability, and today it serves as a standard tool in experiments in quantum optics and quantum information. Another major direction in quantum optics focuses on the interaction between light and matter when both must be described quantum mechanically. One of the most important settings for studying this interaction is cavity quantum electrodynamics. In these experiments, an atom, or another quantum emitter, is placed inside a resonant cavity formed by extremely high reflectivity mirrors. The cavity allows only discrete electromagnetic modes to exist. If the coupling between the atom and one of these modes is strong enough, energy can be exchanged coherently between them. When the system enters the strong coupling regime, the atom and the electromagnetic field no longer behave as two separate systems. When an atom is placed inside an optical cavity and its coupling to the electromagnetic field becomes sufficiently strong, something remarkable happens. The atom and the photon no longer behave as two separate systems. Instead, they merge into a single quantum system, in which energy oscillates back and forth between the atomic excitation and the excitation of the field. This rhythmic exchange is known as vacuum-Rabi oscillations. Remarkably, these oscillations appear even when the cavity initially contains no photons at all. In the quantum picture, even the vacuum is far from passive. The simplest theoretical description of this situation is known as the Jaynes-Cummings model. With just a two-level atom and a single mode of the electromagnetic field, this model predicts a rich variety of phenomena, from the collapse and revival of atomic excitation to the emergence of non-classical states of light. Many of these predictions have been confirmed experimentally with extraordinary precision. Among non-classical states of light, squeezed light is particularly important. The electromagnetic field can be described in terms of complementary components called quadratures, analogous to position and momentum in quantum mechanics. In a coherent state, the uncertainties of the two quadratures are balanced and reach the minimum allowed by quantum mechanics. In a squeezed state, however, the uncertainty in one quadrature can be reduced below this level at the cost of increased noise in the other. The uncertainty principle remains intact. The noise is simply redistributed in a useful way. This is not merely a laboratory curiosity. Squeezed light has become a practical tool in precision measurement. One of the most famous applications appears in gravitational wave detectors such as LIGO. In these interferometers, the quantum noise of light sets a fundamental sensitivity limit. By injecting squeezed light into the interferometer, researchers can reduce noise in the relevant quadrature and push sensitivity beyond the standard limit. As a result, these instruments can detect distortions of space-time far smaller than the diameter of a proton. One reason quantum optics has become such a powerful field is its experimental accessibility. Photons can be generated, manipulated, and detected with remarkable precision. Optical systems can be well isolated from thermal noise, and most importantly, individual quantum events can be observed directly. For this reason, quantum optics has long served as a testing ground for many foundational ideas of quantum mechanics. At the same time, it lies at the center of many modern quantum technologies: quantum communication, quantum cryptography, and several architectures for quantum computing rely on optical systems. Entangled photons can carry information across vast distances. Cavities and waveguides mediate interactions. Optical measurements provide high-fidelity readout of quantum states. Beyond its applications, quantum optics also reshapes how we understand light itself. It shows that the vacuum is not empty, that noise has structure, and that the familiar electromagnetic waves of classical physics are only a special case within a much richer quantum picture. Light, once regarded as the quintessential classical phenomenon, has become one of the clearest windows into the quantum world. Quantum optics does not replace classical electromagnetism. Instead, it contains it. When photon numbers are large and quantum correlations are weak, classical electromagnetic waves naturally reappear. But when individual photons are observed, when correlations become strong, or when precision approaches fundamental limits, the quantum nature of light becomes unavoidable. For this reason, quantum optics is not a narrow subject. It is a domain where the abstract principles of quantum mechanics become visible, controllable, and usable. Here, the boundary between classical and quantum descriptions of the world becomes most clearly exposed. One of the deepest differences between classical thinking and quantum mechanics lies in the very concept of particle identity. In everyday life, two objects may look identical, yet still be distinguishable by their histories. Two identical coins can be marked and tracked separately. Quantum mechanics does not allow this viewpoint. At the fundamental level, identical quantum particles are truly indistinguishable. Labeling one particle or another carries no physical meaning. If we exchange the positions of two identical particles, the physical state of the system does not change. From this simple requirement, a strict mathematical rule emerges. When two identical particles are exchanged, the quantum state of the system can respond in only two possible ways. It either remains unchanged, or it changes sign. If the state remains unchanged under exchange, the particles are called bosons. If the state changes sign, they are called fermions. In three-dimensional space, no third possibility exists. The consequences of this classification extend throughout physics. Bosons are particles with integer spin. Photons belong to this group, along with force-carrying particles like gluons and even some composite particles such as certain atoms. Because their states are symmetric under exchange, there is no limit to the number of bosons that can occupy the same quantum state. They naturally tend to cluster together. Fermions, by contrast, carry half-integer spin electrons. Protons and neutrons belong to this category. Their states are antisymmetric under exchange, and this antisymmetry leads to an extraordinarily powerful consequence. if two fermions attempt to occupy the same quantum state, that state simply vanishes, not because of repulsion or interaction forces. It simply does not exist in the space of allowed states. One of the most fundamental principles of quantum mechanics carries an almost absolute consequence. No two identical fermions can occupy the same quantum state. This rule is known as the Pauli exclusion principle. It does not arise from repulsive forces or from any dynamical interaction. Instead, it emerges purely from the symmetry properties of the wave function. When identical particles are exchanged, the consequences of this principle extend far beyond what one might first imagine. If electrons were not constrained by the Pauli exclusion principle, they would all collapse into the lowest possible energy level around an atomic nucleus. There would be no electron shells, no atomic structure, and no periodic table. Chemistry as we know it would simply not exist. Instead, because electrons are fermions, each electron must occupy a different quantum state. As the lowest energy states fill up, additional electrons are forced into higher levels. From this layered arrangement arise the electron shells, and from them the chemical properties of atoms. The same principle reveals its power in some of the most extreme environments in the universe. In white dwarf stars, electrons are compressed to enormous densities. The low energy states are already completely filled. So if matter is compressed further, the electrons must occupy states with extremely large momentum, which requires immense energy. The result is a special form of pressure degeneracy, pressure strong enough to resist gravitational collapse and stabilize the star. Remarkably, this pressure does not depend on temperature. It is entirely a quantum effect. Even in ordinary materials, the Pauli exclusion principle quietly shapes the properties of matter. In metals, electrons fill quantum states up to a characteristic energy known as the Fermi level, forming what is called a Fermi sea. The way these fermionic states are filled and the ways electrons can move between them determines whether a material behaves as a conductor, an insulator, or a semiconductor. Bosons, by contrast, behave in a completely different way. Because they are not constrained by exclusion, they can share the same quantum state. When the temperature becomes sufficiently low, a collection of bosons can undergo a special phase transition known as Bose-Einstein condensation. In this phase, a large number of particles fall into the same lowest energy state. Their individual wave functions overlap, and the entire system begins to behave as a single quantum entity. This phenomenon was predicted in the early days of quantum theory, but was only observed many decades later. Once techniques for cooling atoms to extremely low temperatures became available, when condensation occurs, quantum effects become visible on a macroscopic scale. Matter waves interfere, and phase coherence extends across the entire system. Similar collective effects appear in other exotic states of matter. Superfluidity is a striking example. Below a critical temperature, a liquid can flow with zero viscosity. It can climb the walls of its container, pass through extremely narrow channels, and maintain motion without dissipation. In this state, circulation becomes quantized, and vortices can exist only with discrete values of circulation. These vortices are not random disturbances, they are unavoidable consequences of the quantum structure of the state. A closely related phenomenon is superconductivity. In a superconductor, electric current can flow with no resistance. This does not happen because electrons move freely as individual particles. Instead, electrons pair up to form Cooper pairs. Although electrons carry the same charge and obey the Pauli exclusion principle, under suitable conditions they can bind indirectly through interactions with vibrations of the crystal lattice. Each Cooper pair consists of two fermions, yet the pair as a whole behaves like a boson. Because of this, many pairs can condense into the same collective quantum state. When this happens, electrical current can flow through the material without scattering, and resistance disappears. The theory that explains this phenomenon is known as BCS theory, which shows how even a very weak, attractive interaction, mediated by lattice vibrations, can produce the superconducting phase. Superconductors display remarkable effects. Magnetic fields are expelled from the interior of the material. Currents can persist almost indefinitely, and quantum phase coherence extends across macroscopic distances. This coherence becomes especially striking in Josephson junctions, where two superconductors are separated by a very thin barrier. Cooper pairs can tunnel through the barrier, producing a current that depends directly on the phase difference between the two superconducting states. The sensitivity of this effect is so great that it forms the basis of some of the most precise measurement technologies ever developed. What connects all these phenomena is not a new force, but quantum statistics. The distinction between bosons and fermions originates from the symmetry of the quantum state under particle exchange, and that difference alone is enough to shape the behavior of matter across every scale. In quantum mechanics, the indistinguishability of identical particles is absolute. It is not an approximation or a mathematical trick. If two particles are identical in all their physical properties, the theory does not allow them to be labeled even in principle. Any attempt to do so leads to predictions that contradict experiment. In certain special two-dimensional systems, even more exotic forms of statistics can arise. Particles known as anyons can obey rules that are neither purely bosonic nor purely fermionic. They appear in quantum Hall systems and are currently being studied as a potential foundation for fault-tolerant quantum computing. These systems reveal a deep connection between spatial dimensionality, particle statistics, and the topological structure of quantum systems, even without considering such exotic cases. Quantum statistics already permeates the physical world. The stability of matter, the richness of chemistry, the structure of stars, the properties of metals, and the existence of superconductivity all depend on it. In classical physics, particles can always be distinguished. Quantum mechanics replaces that assumption with something far stricter. Identical particles are not independent individuals with their own identities. They are excitations of underlying fields. What matters is not which particle is where, but how many particles occupy each quantum state. As one looks deeper into quantum mechanics, it becomes clear that its seemingly simple abstract rules give rise to almost the entire structure of the physical world. Quantum statistics is not a strange detail added to the theory. It is the reason matter has structure, the reason atoms exist, and the reason the universe does not collapse into a featureless, chaotic lump. Yet at a certain point, ordinary quantum mechanics begins to reach its limits. It works perfectly when describing systems with a fixed number of particles evolving smoothly in time. But the real universe does not follow such a simple framework. In high-energy collisions, particles can be created or destroyed. Radiation can turn into matter, and matter can transform back into radiation. If one tries to describe such processes using a theory that assumes the number of particles is always constant, the description quickly becomes awkward. The solution emerged when the perspective was changed at a fundamental level. Quantum field theory no longer treats particles as the basic entities. Instead, it places fields at the center of the picture. In this view, particles are not tiny objects that persist through time. They are simply excitations of underlying quantum fields. Each type of particle corresponds to a field that extends throughout space. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. When a particle is created, what actually happens is that the corresponding field becomes excited. When the particle disappears, that excitation vanishes. In this way, particle creation and annihilation become completely natural processes. The language of fields also fits naturally with special relativity. In relativistic physics, no signal can travel faster than light. and spacetime must be treated as a unified structure. Fields distributed across spacetime provide exactly the right framework for this. Interactions become local interactions between fields at specific points in spacetime, and causality is automatically preserved. The simplest and most successful example of this framework is quantum electrodynamics (QED). This is the quantum field theory describing electromagnetic interactions. In QED, there exist electron fields, positron fields, and photon fields, along with precise rules governing how they interact. When an electron emits a photon, it is not a particle throwing another particle outward. Instead, it is an interaction between fields, where energy and momentum are exchanged in discrete amounts. What makes QED particularly astonishing is its precision. It may be the most rigorously tested theory in the entire history of science. A famous example is the magnetic moment of the electron. Quantum field theory predicts a tiny deviation from the classical value, caused by quantum fluctuations of the electromagnetic field surrounding the electron. This prediction matches experimental measurements to about 10 significant digits, a level of agreement rarely seen in any scientific discipline. To perform calculations in quantum field theory, physicists often use a graphical notation known as Feynman diagrams. These diagrams are not literal pictures of events unfolding in spacetime. Instead, they are visual representations of terms in a mathematical expansion. In these diagrams, lines represent propagators, mathematical functions describing how the influence of a field spreads between points in spacetime. Vertices represent interactions between fields. Each diagram corresponds to a specific mathematical expression contributing to the probability amplitude of a physical process. It is important not to interpret these diagrams too literally. The internal lines in the diagrams do not represent real particles flying around unseen. They are intermediate terms within integrals. These objects do not obey the usual energy-momentum relation of real particles. The phrase virtual particles is often used to describe them, but this is only a convenient shorthand. Feynman diagrams are essentially organizational tools for calculations. They allow complex problems to be broken into manageable parts, making it possible to compute scattering probabilities, decay rates, and radiative corrections systematically. However, the earliest versions of quantum field theory faced a serious problem. Direct calculations often produced infinite results. Quantities such as mass and electric charge appeared to diverge to infinity when calculations were carried out fully. This was not merely a technical inconvenience. It threatened the consistency of the entire theory. The way out of this difficulty is known as renormalization. At first glance, it might seem like a mathematical trick, but in reality, it reflects a deeper physical idea. Quantities such as mass and charge are not fixed absolute numbers. Their values depend on the energy scale at which they are measured. When a particle is probed at very high energies, it interacts with countless quantum fluctuations of surrounding fields. These fluctuations alter the effective values of physical properties. Renormalization provides a systematic way to account for these effects. The infinities appearing in calculations are absorbed into redefinitions of the parameters, leaving behind finite, testable predictions. As the energy scale changes, these parameters run with the scale. They vary continuously with energy. This is not a flaw of the theory, but a prediction that has been confirmed in many high-energy particle experiments. The most comprehensive application of quantum field theory is the Standard Model of particle physics. This framework describes all known fundamental particles and forces except gravity. In the Standard Model, matter is divided into two main groups, quarks and leptons. Quarks form protons, neutrons, and many other particles, while leptons include the electron, muon, and their corresponding neutrinos. The fundamental forces arise from interactions with other fields. The electromagnetic force is mediated by photons, the weak force by the W and Z bosons, The strong force is mediated by gluons and described by a field theory called quantum chromodynamics (QCD). One remarkable feature of QCD is asymptotic freedom. At very high energies, quarks interact weakly and behave almost as free particles. But at low energies, the interaction becomes extremely strong. Leading to confinement, quarks are never observed individually but are always bound inside composite particles. Even the masses of particles have a subtle origin. In the Standard Model, many particles are not simply assigned mass. Instead, they acquire mass through interactions with a special field known as the Higgs field. When the Higgs field undergoes spontaneous symmetry breaking, particles interacting with it gain mass, while others remain massless. This mechanism was confirmed experimentally with the discovery of the Higgs boson. But quantum field theory is not merely a catalogue of particles. It is a unified language for interactions, symmetries, and conservation laws. Gauge symmetries determine the form of interactions. Renormalization describes how the theory changes with energy scale, and throughout the entire structure, fields replace particles as the fundamental entities. Even so, the theory is not the final answer. It is extraordinarily successful, yet it still does not include gravity. Attempts to quantize gravity using the same methods encounter deep difficulties, suggesting that new ideas may still be required. Despite this, quantum field theory remains an extraordinary intellectual achievement. It unites quantum mechanics, special relativity, and symmetry principles into a single coherent framework. It explains how particles can be created and destroyed. It predicts phenomena with astonishing precision, and it reveals that what we call fundamental particles are actually small ripples on deeper underlying fields. Within this picture, even the vacuum is not empty. It is the lowest energy state of all the interacting fields combined. It constantly fluctuates. It influences the properties of particles. It shapes what processes are possible in the universe, rather than a universe built from tiny solid objects. Quantum field theory describes a world made of continuous fields and their discrete excitations. In that world, particles are no longer permanent things. They are events. In the modern picture of physics, fundamental interactions occur at extremely small points in space-time. They are strictly local, yet their consequences can spread across an entire system. This perspective has become one of the most effective ideas of 20th century physics. It lies beneath everything we currently understand about elementary particles and natural forces, guiding decades of experimental exploration. If ordinary quantum mechanics describes how systems evolve in time, quantum field theory answers a deeper question: what those systems themselves are made of. And the answer is not tiny solid particles, but structured possibilities embodied in fields. These principles do not live only in equations. They appear wherever nature operates at small scales, often quietly supporting technologies that have become familiar in modern life. A clear example is quantum tunneling. In classical physics, if a particle encounters a barrier higher than its energy, its motion simply stops. In quantum mechanics, however, the particle's wave function does not end abruptly at the boundary. It penetrates into the barrier and gradually decays. If the barrier is thin enough, part of that wave function can extend all the way through. The result is a real probability that the particle will appear on the other side, even though it never possessed enough energy to cross the barrier in the classical sense. This effect is far from rare. It explains alpha decay, where particles escape from atomic nuclei by tunneling through the nuclear potential. It underlies tunnel diodes and many modern electronic components. It is also the operating principle of the scanning tunneling microscope, a device capable of imaging surfaces atom by atom by measuring a tunneling current exquisitely sensitive to distance. Without tunneling, instruments like this simply could not exist. At the collective scale, quantum mechanics produces even more striking effects. One prominent example is the quantum Hall effect, when electrons are confined to a two-dimensional system, cooled to extremely low temperatures, and placed in a strong magnetic field. Their behavior reorganizes into a completely new structure. In the integer quantum Hall effect, the resistance measured perpendicular to the current takes on precisely quantized values. These values do not depend on defects in the material, the shape of the sample, or microscopic details. Their accuracy is so remarkable that they are used in practice as standards for measuring electrical resistance. The origin of this phenomenon lies in topology. The electronic states are characterized by global quantities known as Chern numbers. These quantities cannot change continuously. They shift only in discrete steps. That property locks certain physical observables into exact values. In such systems, electric current does not flow throughout the entire material, but instead travels along its edges. These edge states are remarkably robust, resisting scattering and allowing current to propagate with almost no dissipation. Even more unusual is the fractional quantum Hall effect. Here, strong interactions between electrons create entirely new collective states. The excitations of the system behave like quasi-particles carrying fractional electric charge. These quasi-particles obey a special type of statistics neither purely bosonic nor fermionic, known as anyonic statistics. Because their properties are protected against local disturbances, they are being investigated as possible building blocks for fault-tolerant quantum computers. Quantum mechanics also shapes the fundamental limits of precision measurement. When many independent probes are used, measurement uncertainty typically decreases with the square root of the number of probes, a rule known as the standard quantum limit, arising from unavoidable quantum noise. But quantum mechanics allows something more remarkable. The probes can become entangled with one another. When entanglement is exploited, noise can be redistributed advantageously, and in principle measurement precision can approach the Heisenberg limit. Such improvements are not merely theoretical. Squeezed light has been used in gravitational wave detectors to reduce quantum noise. Atomic clocks employ entangled states of atoms to improve time measurement precision. These technologies function by exploiting effects that have no classical counterpart. At extremely small scales, even thermodynamics must be reconsidered. Traditional theories assume large systems and small fluctuations. Quantum systems violate both assumptions. Fluctuations become unavoidable, and measurement itself can disturb the system. Quantities such as work and heat are no longer definite numbers, but become statistical variables. A remarkable relation in this context is the Jarzynski equality, which connects the statistical distribution of work in non-equilibrium processes with the free energy difference between equilibrium states. Surprisingly, this relation remains valid even when the system is far from equilibrium. Quantum versions must also account for coherence and the influence of measurement, revealing deep connections between information and thermodynamics. Researchers have even begun constructing quantum heat engines at microscopic scales, where the working substance might consist of a single atom, a spin, or a superconducting circuit. These systems raise new questions. Can coherence improve efficiency? Can entanglement become a thermodynamic resource? And what limits are imposed by control and measurement? Another subtle concept in quantum mechanics is the geometric phase. When a quantum system evolves and eventually returns to its original physical state, it may accumulate a phase that depends not on how long the process takes, but on the path traced in its state space. This phase, commonly known as the Berry phase, can shift interference patterns and alter observable quantities. A closely related phenomenon is the Aharonov-Bohm effect. An electron can move through a region where no electromagnetic fields are present, yet still acquire a measurable phase if electromagnetic potentials exist elsewhere in space. This demonstrates that in quantum mechanics, The electromagnetic potentials themselves, not just the fields, carry direct physical significance. Even after more than a century, quantum mechanics remains a developing theory. Quantum computing seeks to build fault-tolerant machines capable of solving problems beyond the reach of classical computers. Quantum simulation uses carefully controlled quantum systems, such as ultra-cold atoms or trapped ions, to model complex many-body systems. Fundamental questions also remain open. The measurement problem has not yet found a universally accepted solution, and multiple interpretations of the theory continue to coexist. Some proposals even attempt slight modifications of the theory itself, and experiments designed to test them are still ongoing. Perhaps the deepest challenge is reconciling quantum mechanics with gravity. General relativity treats space-time as dynamic, while quantum mechanics typically assumes a fixed background time. Bridging these two frameworks has proven extraordinarily difficult. Approaches such as quantum gravity, string theory, and loop quantum gravity attempt to address the problem, but a complete theory has not yet emerged. What stands out is not the number of unanswered questions, but the extraordinary robustness of quantum mechanics. From atoms to stars, from microelectronics to gravitational wave detectors, the same set of principles continues to operate with astonishing precision. If it sometimes unsettles classical intuition, that is not because the theory fails, but because it compels us to see the world differently. Phenomena such as tunneling, topology, entanglement, coherence, and geometric phase are not peripheral details. They are embedded within the structure of the quantum world itself, and the open questions at the edges of the theory are not signs of weakness. They are signs of depth, more than a century after its birth. Quantum mechanics is still unfinished. It continues to unfold, and while it may not promise comfort for classical intuition, it consistently offers something else: precision. Again and again, that promise has been kept.